All right. Hi, everyone. Welcome to lecture 23. I'm glad you all came despite the fact that this is not in the homework. So there's no more homework. That's great. So today we can just have fun, right? And today, to complete the topic, like the series of all different models of algorithms, we're going to talk about distributed algorithms, which is a different setting than everything that we have been talking about so far, right? So, okay, today we're going to have some administrivia as usual, like the small one. And then we're going to first talk about the different models in distributed computing, which in a certain sense, like distributed computing, like the definition of the models is sometimes like as important as the problems themselves. And then we're going to see one of the kind of most famous problems in distributed computing, which is consensus with Byzantine failures, which is very popular right now. All right. So again, please evaluate the course. Like evaluation is open until December 7th. Even if you don't want to evaluate the course like this, you can just pop out in office hours and just give me feedback, as some of you already have done. And this feedback is actually great. Yeah, and it would help me to kind of figure out what worked and what didn't work for the course. And let the school know that I was a good boy this term. Hopefully I get a Christmas gift. So, anyways, all right. So let's dive into distributed algorithms, right? So what are distributed algorithms? So these are algorithms which run on a network, or you can think of multiprocessors within the same computer, which share some memory or resources, okay? And what are the problems that these that distributed algorithms is concerned with, right? So problems that they solve are resource management problems, mostly like data management and transmission. They also have to deal with synchronization issues, right? Because if you're on a network, you like the computers to be synchronized, like this gives you a lot of advantage algorithmically. And sometimes you also want the, computers or processors in network to reach a consensus, right? And there's many more problems. Okay, so this is pretty fundamental, like distributed algorithm is pretty fundamental. Now, what are the challenges in this setting, right? So the challenge in this setting is that there's a lot of concurrent
Did Rafael leave?
Yeah, I think he got disconnected.
Oh, did his computer crash or something?
I don't know.
All right, can you hear me?
Yeah.
All right, just as I was talking about failure and recovery of processors in channels, apparently my computer fault is my computer fault, and then now I got disconnected. So I'm connecting from my phone, but let me see if I can reconnect my computer.
Yeah, we don't see a screen.
Yes, exactly, because I'm on my phone right now, just to have it's just experienced, right? So there are challenges in this setting as some nodes and processors or computers can fail. And then we have to deal with failure and recovery of these processes in channels, right? So now you're experiencing firsthand the importance of distributed algorithms. All right, so, and with that, with all of those problems, it comes actually many models, right? That will actually be theoretical underpinning of many types of situations in which a network of multiprocessors like can be in, right? So here are the models, and within the models, we have three things to consider, okay? So what are the three things to consider? The three things to consider are memory and communication. And what is that? Like, do the computers or processors, let me just say that each computer will be a processor. Let me just say that from now on. So do the processors have a shared memory? And if they do, it's one model, and another model is like, well, how do they communicate? They may not need to share memory, but they can communicate via message passing. So each processor can send message to a subset of other processes in the network, right? So this is one consideration that you have to have in your model. And the other one is the timing of the messages, right? So do the processors communicate in a synchronous way? And what do we mean by a synchronous way? We mean that there will be rounds of communication. So let's say, one way that you can synchronize is you can say, okay, let's say all of us are in the same location, and we can say, oh, after like every day, we're going to send one message to, whoever we want to send a message, right? So like at midnight, once midnight strikes, like the new day comes, like we can send a message to somebody else. And this synchronizes all of our communications, right? Because we know when we're going to send messages, and these will be the rounds. Or the timing could be asynchronous. So we can send messages whenever we would like. And another setting could be like a mix between the two, which is the partially synchronous model. Okay, and how do you model this partially synchronous model? Well, you can have bounds on message delays, right? Because if I send asynchronously, maybe perhaps what happens is this message will not arrive to you at, one round, but it may arrive like 3 rounds later, and you can have a bound on the message delay. You can also have like processor speeds and clock rates that allow you to partially synchronize network. And the third main consideration that we need to have is failures, like how we're going to handle failures within our network, right? So here, there could be processor failures, and the processor failures can be of two kinds. One processor like may just stop, like it just happened to me, right? Or it can be a Byzantine failure. And what is a Byzantine failure is, let's say that a hacker, a malicious agent, like a hacker may actually get control in your computer and then use it to undermine what the network's trying to achieve, right? So that's what the Byzantine failure model is. And there could also be failures in communication, that messages could be lost or altered, okay? And the other one, it could be like the whole system state, like there could be a system state corruption, right? If you have like shared memory, okay? So these are failures that we have to be kind of aware of, right, for our models. Okay, any questions so far on all these models? Okay, so there's no questions. So today we're going to study a little bit like the synchronous model, right? So here the processors are going to be vertices of a directed graph, okay? And okay, now let's see what the synchronous model, what does it comprise of each of the elements that we just discussed in the previous slide. So in the synchronous model, we're going to assume that each processor has its own memory, so they do not share memory. And since they don't share memory, what is the communication model? Well, each processor can send messages to its outgoing neighbors, okay? And the timing here will be that processors will communicate in synchronous rounds. There will be rounds. And failures here, we may or may not have failures, okay? So we're gonna see both settings today, where we have failures, where we don't have failures in the beginning, and then where we have failures, which is the Byzantine model, right? So here's an example of a network. So let's say that we have perhaps like 4 nodes, and then this node can talk to this one, this node can talk to this one, this node can send messages, and here, those two can send messages like that. Okay, so the outgoing edges are exactly what? Like node 1, so let's say node 1, 2, 3, 4. Node 1 can send messages to node 2, but node 2 can only send messages to node 3, and so on. Okay, so and usually what we're going to have is, let's say, for example, with nodes 1 and 4, they can send messages to one another. Instead of representing it by both arrows, we can just represent it by like an undirected edge. Okay, so if the graph is undirected, all we mean is that the communication can be bidirectional, right? So both of the nodes can communicate with each other. Okay, so this is the synchronous model. Any questions so far? Okay, so and now let's talk about how to mathematically model each processor, right? So and how do they communicate? So first, we're going to agree on a message alphabet, right? So there is a common message alphabet that everybody knows. Usually it's like, you know, bits 0 and 1, right? You can communicate bits in every round. And we also have a special symbol, which is like a symbol to abort, which we're just going to say like it's perp or an abort symbol, right? Like we have seen before in the zero knowledge proofs. All right, and now for each vertex, how can we model a processor, right? So a processor here will consist of, well, a non-empty set of states, right? Because each processor can be in particular states. And then it will have, from all these set of states, it will have a special state, which is the start state. And now, the only things that the processor can do in terms of distributed computing that we care about, right, is to have what? Well, is to send messages, right? So each processor can just say, oh, I know the neighbors that I can send messages to, the other nodes. So the processor can just has a function that, given its current state and given an element, so out of I here, let me just, so out of I is the set of outgoing neighbors of node I, right? So each node knows its set of outgoing neighbors, and then depending on your set of states and the neighbor that you want to communicate with, well, there's a function that says, okay, if I'm in this state and I want to communicate with this neighbor, I'm going to send a particular symbol, right? Which is like, I'm going to communicate to my neighbor, whatever. Does that make sense? And my communication only depends on my state and with who I'm communicating with, right? It's like, what message do I want to send to my neighbor? Well, that's encoded by this message function mu of I, right? And another thing that we would like is that, well, we model each processor by their states. So what we'd like to have is that here is your transition function, right? Where this set here, okay, this ugly notation that I wrote here to the n of I. So first of all, n of I is just the set of incoming neighbors of node I, right? So these are all the nodes that can talk to me. So this is the set of all the nodes that can talk to me. So what's going to happen, right? After every round, all my neighbors that can talk to me, they will send me some message. And when they send me a message, based on the new information that I got, I'm going to update my state, right? And this is what this like function tau of I is actually doing, right? So this is like the set of messages that I may get, in each round. Does that make sense? So all we can do is this, right? So all our processor can do, like mathematically, like in the model that we're going to have, is I have a certain state and I start in a certain start state. And then at every round, based on my state and my neighbors, I communicate to my neighbors. And then now some information has been exchanged. And now once this information has been exchanged, based on the information that I receive, I update my state, and then we communicate again until we reach the end of the algorithm. Does that make sense? Yeah. Any questions? Okay, so then if this is clear, we can keep going. And okay, so now we know how to mathematically model our processors. And what is the complexity measure? How do we analyze how good an algorithm is, right? So the analysis here, like the golden goal, will be like the number of rounds or the total data communicated needed to solve a problem, right? So what we want is to, given a problem, we want to exactly characterize what's the number asymptotically, right? What's the number of rounds or the total data communicated needed to solve this problem. Okay, and it's important to realize that in the synchronous model, right, all we care about is what is the number of communications or the number of rounds needed to communication or the total communication that we need to solve the problem. We don't care about the computational complexity of the tasks that each node is trying to solve. We usually tend to think those are really cheap, and really the expensive resource here is communicating. Does that make sense? So for the purpose of this lecture, we're going to assume that like the processors have unlimited internal resources. Like they can compute anything, they have access to as much memory as they want, and the only thing is that they have to communicate with each other, right? Like that's the real kind of cost, like the real resource that we're trying to get a handle on. Okay, and for today, we're just going to assume that each processor is deterministic, okay, just for simplicity. But you can see that processors can also have randomness, okay, like internal randomness. Okay, so far so good.
So they can solve like each processor can do exponential problems too.
They can do uncomputable problems. They can do whatever they want. Yeah,
like, they can do uncomputable, like okay, halting problems too.
Yeah, exactly. Everything is fair game in this setting because it's just kind of, in the end, as you will see, like these problems will require them to communicate. And what we're trying to figure out is like, even if they're super powerful, how can they, like, what is the minimum communication that is needed for them to achieve a certain task, right? For example, to achieve consensus, like, you do need to communicate, you do need to send messages. And even if you had like the extreme computational power, like, we want to figure out like, what is the minimum communication that can be achieved? Does that make sense?
Okay, yeah.
Yeah, and this of course is for simplicity, right? Because you can probably try to achieve also, you can require the processors to be polynomial time machines, but usually in these tasks, like it turns out that whatever they need to whatever problems they need to solve themselves, they're actually quite simple. So like this assumption that they have unlimited internal resources is not like is not super great. Even though today actually you're going to see that for the Byzantine algorithm, like the first Byzantine algorithm, we actually need exponential memory. Okay, so and if you don't, actually you need to use a different algorithm, but that one is much more sophisticated. Okay, so we just need to keep that in mind. Okay, but that's an excellent question, by the way. Yeah, like this will affect, as you're going to see in the second part of the lecture, but for simplicity today, let's just, for simplicity, assume that they can do whatever. Okay, so all right, so now let's look at a simple example of a distributed computing problem, which is the leader election problem. And in this leader election, you can think of like, oh, if I have a network, if I start with a network, how can I break symmetry in this network, right? So that's essentially like the question of electing one node to be the leader. So, and the input here is a network of processors, and what the output, what do we want, right? So we want to distinguish exactly one processor, which is the leader of the network, okay? All right, so, and what is the motivation for leader election in networks, right? So, well, usually, the motivation here is that the leader can take charge of communication, of coordination, of allocating resources and other tasks. And it's quite used, for example, when you're trying to coordinate like robots in a network that are just trying to accomplish a certain task, okay? So that's very common there, very practical. And let's just consider the very simple case that we have a ring network where in this ring network is like a circle, right? And then we have bidirectional communication, which means that our graph is kind of an undirected graph, right? So here's an example of a ring network, which is going to have 6 nodes. Like, I'm just going to name the nodes just so that we can talk about them, but the processors, they don't have these numbers, okay? This is just for us to communicate. So 1, 2, 3, 4, 5, let's say 6, and 1 can talk to 2, and vice versa, right? So the network is this ring. Does that make sense? So one can talk to two and two can talk to one, and each of them can only talk to their immediate neighbors. Okay? Does that make sense? So we have this ring network, which is symmetric, and we have this bidirectional communication, which makes it really symmetric, and the processors are numbered clockwise, but just for us, right? They don't know this number. Okay? All right. So here's a fact, right? Which is quite easy to prove. So if all the processors are identical, which means that they have the same set of states and transition functions and the same start state, and if they're deterministic, then it's impossible to elect a leader, right? And why is that? It's because we can never break symmetry from this very symmetric situation. Because if you think about it, no matter what a processor would do, because all the processors are essentially the same, right? They have the same transition functions, the same message functions and everything. What happens is, look at an execution of one round. After one round, each process will send the same messages to its neighbors. And then all of them will update again to exactly the same state, right? So in the state 0, they're all at start state. And then after one round, they're exactly at the same, like, is it different than the start state, but they're exactly at the same state because they all receive the same messages, right? So all these processes are always symmetric after every round, right? So at every time, like no matter how many rounds have passed, you know that all the processors will be exactly at identical states. Yeah. So this is one case, for example, where you need randomness. Randomness is very useful to break symmetry, right? And we already saw another example of this. And remember that I mentioned that there is application in distributed computing when we talked about the isolation lemma, right? Like that's very useful to like break symmetries, right? All right. So, all right. So now let's talk about the leader election algorithm. And let's now assume that each processor also has a unique ID, which we're going to say like that's UID for each processor. They don't know the size of the network though. They only know that there is a unique ID, right? And again, how can we do that in real life? Well, here you can see how randomness can get this. Randomness can get us this with high probability, right? So, all right. So, but they don't know the size of the network here, but let's assume that each processor has a unique ID, right? And now we can say that the processors know the unique ID. And now let's say that the unique ID is the number that we gave to them, right? So 1, 2, 3, 4, 5, 6. Let's say that these numbers are exactly their IDs, right? So now we have our ring network and they have these IDs. So now they're not symmetric anymore because now each of them has a different information, right? All right. So how do we do an algorithm for a leader election now? So is the simplest idea that you can come up with. We can say, you know what? We have our unique IDs. So what we do is each processor will send its unique ID in a message to its neighbors, and then this message will just be relayed like step by step around the ring. Does that make sense? And now what happens, right? So when the processor receives a UID, like a unique ID, it will compare this UID with its own. And if it's bigger than my own, I keep passing it on. And if it's smaller than my own unique ID, I'm going to discard. And since the unique IDs are different, if the message that I receive is equal to my unique ID, this processor will declare itself the leader. And then the leader would just kind of brag about it to everybody else. The leader's like, I'm the leader. Does that make sense? So, all right. So let's see how this algorithm plays out in our ring network with 6 nodes, right? So we have here 1, 2, 3, 4, 5, 6. And each node is doing that like at every point in time, right? So at first, what happens? Let's see the first round in pink. So 1 is going to send a message to 6, is going to send 1. 6 is going to send a message 6 to 1. And in the first round, like 1 sends its own ID to 2, 2 sends its own ID to 1. And then here, the first round, we're going to have this, and so on, right? So we have like 4 is going to send 4, 3 is going to send 3, 4, is going to send 4, 5 is going to send 5, and here I'm going to send 5, and then here I'm going to send 6. So in the first round, everyone just just give to all its neighbors its own ID, right? But now what happens? In the second round, 1 is going to look at the UID, which is 1, and is going to look at the UID of 6 and say, oh, 6 is bigger than me. So now in the next round, which I'm just going to do it in green, 1 is just going to broadcast 6, right? And then, and then 1 just looked at the ID that came from 2, and 1 is, oh, 2 is an ID that's bigger than mine. So then 1 is going to broadcast 2 to 6, right? Because you're just relaying, right? So you're not sending the message back. So I'm relaying it to 2. And now, well, 2 received 1 from 1 in the first round, so it's not going to broadcast anything to 3, right? But 2 is going to broadcast 3 to 1 in the second round, right? 3 does not broadcast anything to 4, right? Because he received 2, which is smaller, right? But 3 will broadcast 4 to 2, right? 4 does not broadcast, so 4 broadcasts 5 to 3. But then you can see that there's no broadcasting kind of going this way, right? Like going this way in the ring, because like 5 is not going to broadcast anything to 6, but you broadcast 6 to 4, right? And 6 never broadcasts anything to 5. Does that make sense? So now what is going to happen, right? As you can see, so what's going to happen here is that everything is stopping at 6. 6 is not talking to anybody. And then in the third round, what is going to happen, right? So let me put it in red. So in the third round, what happens? Well, 6 is not going to send message to anybody, but 1 is going to send 3 to 6, and 2 is going to send 4 to 1, and 3 is going to send 5 to 2, and 4 is going to send 6 to 4, and 5 did not receive anything, so 5 doesn't broadcast anything. Does that make sense? And now, but now what happens? There's another arrow going on here that we didn't draw, which is 2 received 6. So 2 is going to broadcast 6 to 4, which is getting a little messy, but I'm going to write it here. Does that make sense? So now 1 knows that 6 is the highest node, right? 2 already knows that 6, 2 is already relaying that 6 is the highest node that it has seen. And now 3 is going to, so in the end, what's going to happen? What's going to happen is that we have 1, 2, 3, 4, 5, and 6. And in all these rounds, what happened, right? So first 6 sends its ID to 1, and then 1 sends 6 ID to 2, 2 sends 6 to 3, and in the next round, 3 sends 6 to 4, and then 4 sends 6 to 5, and then 5 will send 6 to 6. Now, once 6 receives the message 6, 6 will declare itself the leader, right? So let's say there's another, 6 can just send a special symbol that we had for the leader, and then 6 would just broadcast to its neighbors like, all right, once I know I'm the leader, I'm just going to send the symbol L, let's say, right? And then everyone knows like that 6 is the leader. Does that make sense? Like maybe as a tuple, like L and 6, right? Like, so the leader is 6. Does that make sense? Okay, so now let's analyze the simple algorithm, right? So certainly this algorithm terminates, right? And elects the leader with largest UID, like, and the proof here was proof by example, right? Just because the leader with the largest ID is never communicating with everybody, and everybody will get to see N like at least once, right? Like, which is the leader, and then the leader will declare itself the leader with the largest ID, right? And now, what is the running time of this algorithm in terms of communication? Well, notice that because we're in a ring, what happened here, right? Like we needed N rounds for the element with maximum unique ID to declare itself the leader, right? Because its message has to go around all the N nodes, right? And all the N nodes, because it starts on the leader and has to go back to the leader. Does that make sense? So it has to go around the cycle. So only after n rounds, the element with maximum EID will declare itself the leader. And we know that no other processor will. And then once that happens, right, we also need another like n/2 rounds so that everybody knows that the leader is actually, to know who is the leader. Does that make sense? So here, what happens, right? So what is the complexity of this algorithm? What is the number of rounds? Is O of n, right? Because it takes n rounds for the leader to kind of declare itself leader, and then it takes like n/2 rounds for everybody to know that the leader like is exactly, you know, right? To receive a message saying, oh, the leader is the element with this unique ID. And what is the total communication here, right? The total communication is O of n squared, because in the beginning we have n communications, right? And then we keep going, having like O of n communications like at every point in time, okay? So, and here we can, you know, if you just wanted to analyze the number of rounds, this number of rounds is optimal, but you can actually reduce communication to n log n by successively doubling, okay? And this here, for this, you can just see the reference, okay? So I'm just gonna leave the reference for you to see, like in the end of the lecture. Does that make sense? But so far, so good. Like, was this algorithm clear? And is it setting clear?
Like the analysis just kind of like follows the single number as it goes around.
Exactly. It just follows the biggest number, right? Because that's the biggest number. Well, that's the analysis of correctness, right? But if you want to talk about like correctness and also for the number of rounds, but if you're interested in communication, you have to like account for how many messages got passed. And one way to do this is to say how many times was the number k passed in the network. And you know that this number,
like the communications is, it's only like upper bounded by O(n squared, right? Because like if you have like numbers kind of consecutive around each other, and like after one step you'll need a bigger number, then that feels like it's O of n.
Well, correct, but remember here that we are in the worst case analysis, right?
Yeah.
In the worst case here, we have actually that if you have all the IDs being the same, like being consecutive numbers as I showed, you know that the number of communications is also lower bound by n squared, right? So we know an upper bound, which is worst case, like O of n squared, but you're right? Because the analysis here will be what? Like a unique ID k, right? If it's the k like smallest like unique ID, this unique ID will travel at most like k minus 1 steps, correct? It will be relayed at most k minus 1 times.
Yeah.
And that's how we get the O of n squared, because you just sum now, right? Like you sum, like 1 gets relayed like 1 time, 2 gets relayed twice at most, 3 gets relayed 3 times, and then you have this sum 1 plus 2 plus all the way up to n, right?
Yeah, I see.
And we also have a lower bound for this case in the worst case. Does that make sense?
Yeah.
But for this algorithm, right? And that's what I'm saying. You can reduce the communication to O of n log n by successively doubling, but yeah, I'll leave that for the references because I want to get to the next part. But so far, so good.
Yeah.
But again, yeah, great question. Like, this is not always going to happen, right? Like in some other cases, the communication is much smaller, but remember, we are here in the worst case setting as well. Okay. Yeah. Cool. Any more questions? Okay. So if no more questions, now let's talk about the consensus with Byzantine failures. And I'll start